There we go. Welcome. It is the 10th of April, 2015, and this is episode 2 of the Unseen Podcast. Now, this evening, we had planned to be joined by an expert on cryptocurrency, Dogecoin in particular, and have a discussion about cryptocurrency. We're going to have to postpone that. I think there was a confusion about time zones. So, but I am fortunate to be joined by 3 short order volunteers here. The same people we had last week. Marsha Barnhart. Say hello, Marsha.
Hello, Marsha.
Ciro Villa.
Hello, Marsha. Hello,
Hi.
everyone.
Hey, Paul. Everybody else.
And Nick Nielsen.
Hello, Paul, and thanks for having us on again.
Yes, well, thanks for coming in on short notice, guys. Let's start with a bit of news. As you know, many of you know who follow the Wow Signal podcast, I posted a burst just a couple of days ago about the fast radio bursts, and we'll get into that more later. But one thing I mentioned were the perytons, which are similar to the fast radio bursts, but seem to be coming from a more local source. And I said that was a mystery. Well, it turns out maybe not a mystery, that the folks in Australia have solved that. It appears to be what happens when you open the door of a running microwave oven. So I didn't think they would allow microwave ovens near a radio observatory, but apparently it doesn't have to be all that close, and they still detect these signals. So that's solved, I hope. And but we still have the fast radio burst. We still have the mystery that was discussed on that burst, which I will get into later if the panel wants to talk about it. So what else? Oh, let's start with Nick. Nick, you wrote something, I think you just posted it this evening about, let's see if I can, thinking about civilization. Could you kind of summarize that for us?
I posted a longish piece on my WordPress blog in which I reviewed a number of different exercises or experiments you were in attempting to formulate a theoretical context in which to talk about civilization, hopefully something sufficiently generalized that it can apply to anything in the past and therefore be projected also in the future. So I have often referred to a tripartite distinction made by philosopher Rudolf Carnap between classificatory concepts, which are taxonomies, comparative concepts, and quantitative concepts. And so I reviewed 3 ways that everybody's heard of the Kardashev types, for example. That's a quantitative attempt to give an account of civilizations on the basis of their energy usage. And then I discussed how, when I spoke at the first 2011 100-year Starship that was in Florida, I talked about an alternative scheme for classifying spacefaring civilizations, where I classified them according to their ability to overcome gravitational thresholds from the surface of the Earth up through planets, solar systems, galaxies, and beyond that to the multiverse, if one is willing to go that far. Then I talked about the distinction I've made between clusters and series when talking about the origins of civilizations in the various places around the planet where we've seen independent origins of civilization, whether it be in the Indus Valley, the Yellow River Valley, in Peru, in Mesoamerica, and in Mesopotamia or the Fertile Crescent. You see a whole cluster of different civilizations, and then they come out and form different series that go in different directions. Another framework I talked about is what I call orders of civilization, just to try to distinguish whether we're talking about a particular milieu, as it were, or the whole cycle of a civilization from birth through maturity through decay, or we're talking about the whole structure in which people talk about these things, in which civilizations are interrelated. So it was just a large review piece in which I wanted to talk about some of the different frameworks I've been considering, and hoping to elaborate and go beyond as I develop these ideas.
So where does our current civilization fit into that?
Well, what do we mean by our current civilization? If we mean right now, the planet is pretty much unified in that there's very little area of the planet that falls outside of the global civilization we have now, and that global civilization is ultimately derived from the civilization that emerged from the Industrial Revolution in Western Europe in the late 18th or early 19th century. So I in my most recent blog post thinking about civilization, I suggested we could refer to this growing together of originally separate civilizations as a terrestrial cluster. And when we see a variety of spacefaring civilizations going out in different directions, each of these will form a series emerging from that cluster. So that's one way to think about it.
Yeah. Now, let's think back about, say, 500-600 years ago, there were civilizations that had very little contact with each other all over the world.
Yes, the fellow who is behind strategic forecasting, I can't pull his name off the top of my head right now. He wrote a book. George Friedman wrote a book in which he mentioned that, and I quoted in an early blog post, humanity did not know itself as a whole. And during what historians used to call the age of discovery, when European ships went around Africa and Magellan's mission circled the globe, and the Columbian exchange began in the Atlantic, human beings started to discover each other in their scattered places across the globe, and these conflicts were often unpleasant and bloody confrontations when people reconnected as a single species.
Yeah. So do you think that's sort of analogous to what could happen in the future, or are we going to be too different?
I did speculate that on my second 2012 100-Year Starship presentation, where I suggested that when enough time elapses and spacefaring civilizations have scattered through the galaxy and adaptive radiation has taken place, and we have a variety of different civilizations that have gone their separate ways and lost contact with their origins, when they are rediscovered, it'll probably be a fairly analogous process on a much larger scale. If we make it that far and don't go extinct before that.
Yeah. Well, I have two reasons to be optimistic about what would happen if two civilizations from two different star systems met. One is that they would probably not want the same things, except for energy, which should be abundant at that point. And second is that the distances and the time scales are so long that it doesn't really support, what we would think of as warfare, at least on a human scale. I mean,
there have been some people who have very explicitly made the argument that the warfare would be impossible, but of course there's also people who have explicitly made the argument that interstellar communication is possible or interstellar travel is impossible. There's all kinds of people out there who are willing to say that we're stuck in our solar system and nothing more can be expected beyond that. Right. For example, the authors of...
I'm going to jump in here.
Go ahead.
Sorry.
Go ahead.
I was going to jump in and interject that I often hear people say that they don't think any civilization that Homo sapien might encounter would be, they think it'd be vastly different. I, on the other hand, do not think it would be vastly different. I think just as worlds, planets, are often round. You don't find square planets. You don't find triangular planets. There are forces at work in the universe that create certain patterns. One of them being terrestrial stellar bodies are round. There's a reason for that. Now, I think that is analogous to beings. Beings would probably naturally follow certain patterns. They would come into form following certain patterns, just like gas and debris comes into form following certain patterns, making spherical objects in the heavens. That's why I think that if we ran into, other than Homo sapiens sapien out there, I think they'd probably have limbs and stereoscopic type of peripheral devices, just as we do. I think we'd be a lot more the same than different.
That's the argument from convergent evolution. And some people have taken that quite far and suggested that any other intelligent species would be quite similar to us. And of course, other people disagree. But yeah, sure, we're all going to be driven by the same. Our solar systems are going to be driven by similar sets of physical laws, and biology is going to be driven by similar mechanisms,
Yes.
Natural selection primarily, genetic drift, and the rest of them. And in fact, one of the things I didn't write about in my most recent blog post, but another framework that I commonly use when I talk about civilization is the use of the term peer civilization, near peer civilization, and non-peer civilization. So yeah, if we meet a peer civilization, it's going to be very similar to us, but that's basically the only thing we know how to look for, because if you put up a radio telescope and you listen, obviously you're listening for other people who are going to be broadcasting by radio, so they would have had to have enough of the historical similarity that they would have converged upon that kind of electronic technology.
I'm gonna put it. Sorry,
go ahead.
Sorry, Paul. I was gonna just add that I was gonna play a little bit devil's advocate, so to speak, and propose that we're always anthropocentric in our quest for life, and we have the tendency, obviously, to look for the similar. It makes perfect sense what Marsha argued. It makes perfect sense that we would look for example, we're looking for the existence of water in other places as a foundation for the presence of life. And that makes sense because we know what we know, which is that life needs water, and it started with the presence of water. So we're looking for the water as a base, and then we're looking for carbon-based life. But there's also the consideration that, in my opinion, that there could be internal environmental conditions on a given planet, for example, that could dictate the emergence of a certain species that might not necessarily be humanoid in the way that we think as being humanoid. So I guess my argument, so to speak, is perhaps, and just perhaps, this is all speculative, of course, that might be a possibility that on some planet there might be some civilization that is perhaps not humanoid out there based on the environments that allowed it to emerge. So I guess that's, just
your point is taken on anthropomorphic, but think about this. On this planet alone, we have some very bizarre life forms
exactly
that don't look anything like us.
Right.
Very bizarre. And they were all created in this exact same milieu as we
Right.
were.
Yes.
And look how disparate these entities that live on this earth that we don't even pay attention to are absolutely bizarre.
Exactly.
And yet they're here, and they so I don't know, but what, some other type of entity might be like a starfish or some crab or something. I don't know, but there's an awful wide variety of the life form just existing here that
Right.
I think we could see something that we would recognize.
So
if it was made up of matter, not everything's going to be made up of matter that we would recognize and discern with our senses. I think that too.
Right. So basically, this could be taken in extreme direction. Of course, we're playing speculative right now, and it's fun. It's fun to do, and we can go with our fantasy. We can go in a lot of different directions. Even what I was saying previously, which is that the search for life is based on the existence of water for the most part right now. But there's speculation that there might be non-water based life forms out there. We just don't know.
they may be quite close to us. It could be on Titan.
Exactly.
In fact, when I talked to David Grinspoon,
methane-based.
yeah, well, kind of methane-based, yeah. When I talked to Dave Grinspoon, he's very excited about the possibility for complex, self-organizing chemistry, self-reproducing chemistry on Titan, which is kind of the broad definition of life. And we're seeing we see complex things on Titans.
Many astrobiologists consider it almost inevitable that there'll be some sort of biochemistry either in the moons of Europa or on Titan or on the other worlds out further in our solar system. And obviously that's going to be a very exciting time when we finally get out there with probes or ourselves and can check for that.
Yeah, and we happen to know that, she said so, but Carolyn Porco's group has proposed a biology mission to Enceladus. It's not funded yet, but that, and there's certainly a lot of interest in a biology mission to Europa, and so now Enceladus has tremendous advantage that we know that it is spewing out geysers of this stuff, so you don't have to drill a hole in it to sample it, so you don't even have to land to sample it.
Yeah,
so
you can swoop down close enough to go through a geyser and pick up some traces and analyze that.
So
now, is that the one that was found to have those? Is that the body, the celestial body that was found to have those two?
No, that's Sirius.
Reflective surfaces.
No, that's
one.
one.
Oh, that's Sirius. Okay, yeah.
That's
and we're already passing by that.
Yeah, the Dawn mission started off visiting Vesta. As a matter of fact, they have provided an enormous amount of data coming from their base Vesta. From when the spacecraft was around Vesta for a while. I don't remember off the top of my head how long the mission lasted, as far as the Vesta portion of the mission. But then, of course, it moved on to Ceres, and as it was approaching Ceres, the imagery started showing these bright spots, which was an exciting mystery. I'm not sure if that's been settled or not.
No, it's not settled. Yeah, they're not in science orbit now. They will be in a couple of weeks, and then they should start getting better images. Right now, they're at a very high phase angle, so they're basically a crescent.
Gotcha.
But that is pretty exciting. It could be some kind of ice volcano or ice geyser, which would, so what you see basically there is water or water ice reflecting the sun, and that would be really, really interesting on such a small body to see that. I don't know if it has biology implications or not, but let's go look.
Exactly.
And in a couple of weeks, we will go look. I think that Enceladus is a moon of Saturn, and I think it's the sixth largest moon. It something like the 9th or 10th furthest out. I mean, closest in. Sorry, and it's close enough to Saturn that there are strong tidal forces inside it that generate heat, and this heat seems to be melting some of the ice inside and producing water geysers or ice geysers. There are clear markings on the surface where the stuff pops out, and it seems to be more or less consistent. So you could send a mission there just to fly through the geyser with the right instruments, and you could capture. I don't know if you'd capture any microorganisms, but you might certainly detect their chemistry. So it could be very exciting. I would estimate that's at least 15 years away, even if it gets funded next week, because it takes a long time to build something like that, and then get it out to Saturn. So, but it's pretty exciting.
How many years is the gravitational trajectory to Saturn?
Oh, geez, I'm not sure exactly. It's probably a straight transfer out there. Probably a good 10 years. Right. It's really, it depends on if you get a small enough satellite and a big enough rocket, you could, with a good propulsion stage on the other side, you could get out there faster. What they did with Cassini was multiple flybys. Yeah, they did multiple flybys with Cassini to get it up there, so that actually took longer. So
speaking of getting a fast rocket, a friend told me that NASA has started funding the Casimir ion rocket engine. Is that true?
Yeah, well, they funded a small study. I don't know how much hardware they're going to build on that money. Maybe a very small thrust demo. The problem with Casimir is the same problem you get with any ion engine. You need a lot of electrical power to get any decent thrust out of it, and that begs the question of where that power is coming from. Not going to come from solar panels. They'd have to be enormous. So, this says, well, okay, back many years ago, we developed nuclear reactors that could operate in space. Nothing very big. I think the Russians were the biggest one, which was about 5 kilowatts.
And they're very dependable for long-term generation of small amounts of power. They're just by decay.
Well,
they just generate by warmth.
Yeah. Well, those are the radioisotope thermal generators that they generate a few hundred watts.
Right.
They're not fission reactors, though. They are just.
They generate electricity from the decay and the heat.
Right. That's exactly right. Yeah, they basically use the coldness of space to generate electricity across that thermal gradient. But a fission reactor, like actual nuclear reactor, could generate in principle megawatts. But nobody's built one bigger than a few kilowatts. The Soviets flew one, I think, called Topaz back in the 60s or 70s. I'd have to go look it up. But Topaz, I think, flew once or twice and generated a few kilowatts and made a big mess when it landed in Canada. I'm not sure what happened there exactly, but assuming you can get over all the objections that you're going to get to nuclear power in space, irrational that it might be, you need to invest billions of dollars to make that happen. Now, if you did that, if you could generate megawatts in space, you could use something like Casimir to make interstellar missions a lot shorter.
Or interplanetary missions pretty routine.
Well, yeah, I'm sorry, I shouldn't. Interplanetary missions, sorry. I didn't mean interstellar.
Okay.
Don't you kind of think that billions of dollars haven't already been invested?
Well, we actually know how to make.
Have already been invested.
I'm
talking in black programs.
But we know how to make
there's been a tremendous amount of money.
Not megawatt levels, no.
But we make great megawatt level fission reactors that are in aircraft carriers and nuclear submarines. The only reason they're not used in space is political. Number one, because the public hates it, and number two, because of the proliferation concerns. If it weren't for the proliferation concern and the concern over radioactivity and radioactive waste, we could have a very active nuclear rocket program, and we could be going into space regularly at a much lower cost than chemical rockets.
Right. There was something developed in the 60s called NERVA.
Right.
Which
and
Dumbo. NERVA never flew, but it was demonstrated on a test stand, and it was a very, very high thrust, high specific impulse engine. And it was, it was just the first generation. It could have been even better.
If you look into what was done in the 60s in terms of researching nuclear rockets, there are literally dozens of designs that are out there that were never built. They were only speculative. But if we were to pursue the technology and development, we could develop it. We could probably do pretty well by it.
As a matter of fact, more recently, when NASA was exploring the previous Constellation program, you might know that, Paul. There was a period of time I remember that there was this bimodal nuclear thermal rocket that was being kind of publicized quite a bit, and there used to be an animation that was circulating on the internet. I think it was about 5 or 6 years ago. I think that was when they were still working on the Constellation program before it spun off into the current state, with the space launch system, et cetera, et cetera. There was this particular design that was based on nuclear thermal energy.
Right.
So
yeah, I guess I don't know much about that, but yeah, I mean, the physics of it is not mysterious at all. We know how to do it, but you just
right.
To make a spaceborne one that flies and is safe, you're going to have to spend a lot of money, probably more money than they spend in the James Webb Space Telescope, or are spending on the James Webb Space Telescope. So.
Well, yeah, I mean, obviously the financial aspect, and I know we're kind of jumping from one subject to another here, but the financial aspect is always a challenge and an issue when it comes to, be able to get the funds for some of these things, because there's always the public perception and the political difficulties, historical, that that we have to face, and we've been facing, and we still face, to be able to convince a certain amount of the political elite and even the population, that these missions are important. And it's hard to see the value of space exploration on Earth. You have to really explain it to people, and even then there's a lot of resistance, because a lot of people, they really think that we should you've heard the mantra before, why
Yes.
not spend the money on Earth? Why do we waste the money on pipe dreams in space, so on and so forth? So yeah, that's a major problem, public perception.
But you guys, honestly, I don't want to sound like a wackadoodle here, but now just think about this. Come on now, we already know billions, if not trillions, have been siphoned out of the public coffer and shunted over where the public didn't get to say, oh, I don't necessarily want us to use that type of propulsion engine because I'm worried about it. It took it completely out of the public realm, and have been, I don't know who, but I can guarantee you that billions of dollars have been in a very quiet slush fund working on exactly the things the public would not want to spend money on. It has been spent on. Now the question is, what did they do with that? Because they haven't been spending on B-52s. They've been spending it on something that we don't know about.
Yeah, we know that money.
They are way ahead. Way ahead.
Well, in some things, perhaps. I don't think the military or the intelligence community really care about deep space.
No.
So they're interested. They have spent a lot of money. They care about gathering intelligence and blowing stuff up, right? And
No. What they're interested in they're interested in force multipliers. And if they are out in space and they're owning space, then they're going to spend a tremendous amount of research and energy and resources on owning space. And I'm not just talking about satellites that can fly over and be positioned to spy. We're talking about a long-term presence in space, as probably as far as they can go. That's what happens.
Yeah, I don't, but I still don't think that they don't need the kind of propulsion we're talking about they only care about near Earth stuff.
Why would they not want that kind of propulsion, Paul? What if they could get out to a place that they know they could already mine? They could mine precious metals or whatever. They could already be out there sussing out this type of thing.
Marsha,
suck it off the surface of something.
Well, they don't need to do that. They don't have any requirement. I mean, what they need to do is they do have a lot of different types of missions in low Earth orbit and even in GEO that do cost a lot of money and do require very sophisticated technology. Even technology that you and I don't know about, but what they don't have is any need. I mean, there's no U.S. adversary on Mars. There's no U.S. adversary on Enceladus. They just don't need to be there. There's nothing to see, nothing
Why
to do.
did it matter that we went to the moon, Paul?
Well, that wasn't a military.
What did it matter?
Mission.
It was Cold War competition.
Well, they were
Yeah.
all.
It was symbolic.
So we would have a presence in space, not in low Earth orbit, a presence in space on another body, and we'd like to get to Mars.
But right now, Mars mission would be like the moon mission. It would be a symbolic first that would be have a great deal of impact. But if you don't follow through on it, like we didn't follow through on the Apollo program, you don't have a presence. You know, like Paul said, everything now that matters to people in space is in low Earth orbit and a few things in geosynchronous orbit and higher orbits. But the nation states of the world right now don't have any reason to look beyond Earth orbit except for the scientists among us who are serious about funding missions to gain knowledge that sometimes get funded.
And national prestige. I mean,
we'll have to. We'll have to agree to disagree on that, because I cannot imagine why a world power would not want to force in deep space. I just can't imagine that. I could be wrong, but
there's nobody to fight there.
I think that there's different issues that
I don't know
they're mixing up a little bit here, in my opinion. I mean, of course, they're all correlated to one another, but I think that it's important to make a distinction between, what historically has been called the space race, which it was, it was highlighted during the Apollo era, like you guys were mentioning before, when, especially during the Cold War, when the Russia and the United States was intended to regain its prestige as being the first one to get to the moon. And I mean, it's still present. There's still political interests out there these days, but there's also much more atmospheric cooperation going on, even on the International Space Station. So the political item, it's there, but the military, it's kind of, to me, it's one step beyond. Of course, it's related to political power and and different countries trying to be ahead of one another, But the military, historically, has been very focal to space exploration, and it still is these days. I mean, we know that a lot of the installations that are used for space launches and and a lot of the experience and the knowledge are closely related to military technologies. So there's no denying that. But from that to go and say that there's a need, like Paul was saying, there's not really going to be a need for a pure military presence, at this stage of the game, anyway. Plus, I think that again, the military missions are kind of present, but they're kept away, from scientific missions. They're normally not mixed and matched together to a certain point, I suppose. So my point is that there's different aspects of space exploration that involve, involve the politics, and some that involve the military. But it's important to keep those segregated, in my opinion, anyway.
Yeah.
I don't know.
Yes. Now, they have purely military launches, right? Clearly, they have purely military mission launches, and those don't necessarily get shared. The outcome of that and what their purpose is not shared with the scientific community. So you don't know what they're up to out there.
Well, the scientific community doesn't really care, actually. That's not their. The scientific community doesn't care, except that maybe they might get a slightly cheaper Atlas or Delta because of the military paid for its development.
But a surprising amount of that is shared. I mean, the knowledge that there is a launch, there's a small military unmanned shuttle that goes up on a regular basis, and people know when they're being launched if they care to follow that information. Right. And we have great telescopes that can see satellites in orbit if we want to spend the time to pick out military satellites and monitor them from the ground. So we have a pretty good idea of what's up there and what's going up there and what's coming down.
Yeah,
right. And also, ironically, military technology has been pioneering and spearheading a lot of things in everyday life. I mean, even on Earth, technology and the whole beginning of the internet started off with military technology, as you all might know. So, and going back to the space exploration, a lot of the things that are used for non-military purposes, a lot of the technology started off from military, applications. Why?
Sure.
Because the money was there for military purposes to
Well,
begin with, right?
also, war drives intense competition, right? It's one of the most
Yeah.
intense competitions we engage in. I mean, radar, for example, came from out of war.
Well,
Lots of other things.
Look at the Second World War. When it started, there were no digital computers, there were no electronic, there were no jet engines. Well, there were, but they hadn't even used yet commercially. There were no nuclear weapons. All of these things were developed in the space of 4 or 5 years. Ballistic missiles with the V2, that all came online very quickly. And then after the war, if you read about the science that's going on in the 40s and the 50s, how often you come across people buying military surplus and using it in large science projects is quite remarkable.
Sure.
And you also, the legacy of the Cold War, the mapping of the world's oceans by military submarines, which have revealed the mid-Atlantic trench and was a major evidence for geomorphology or plate tectonics, and other private enterprises also revealed to us, the military is private for governmental reasons, but I believe that the exploration financed by
Yeah.
Pemex, the Mexican oil company, was behind the discovery of the Chicxulub crater off the coast of Mexico, which was the basis of the impact theory of dinosaur extinction. I call that proprietary.
Well, I don't know how we got to dinosaurs, but the fact is that
it's science. Yeah.
technology has been driven by the military wanting to maintain superiority in whatever manner they can. And, I'll just drop that. But I think it's naive to think that there hasn't been extraordinary leaps in technology made by secret military projects now that you guys aren't privy to, and we won't be privy to, because guess what? It ain't our business.
Well,
so I think it's just naive.
Kind of
to
is
think
my
that
business.
We
but
don't have forces right now that can get us to the stars.
Well,
didn't you think that was
military training, for example? That's another example that maybe sometimes we don't think about, and a lot of people take for granted. The training that a lot of people obtain during the military, both in the U.S. space program and also in the Russian space program and other countries' space program. Look how many astronauts have military background. As a matter of fact, at one point before in the past, I think that the overwhelming majority, if not all of the astronauts, were former or current military personnel. Because where do you get the best, most appropriate training? For example, as a pilot, well, you get in the military. So that's another point of correlations between the military world and the defense world with the space and space exploration world, if you want.
Well, okay. So, I mean, Marsha, I would just say that, I know there's a lot of advanced technology being developed in the black world. And a lot of it has to do with intelligence gathering. A lot has to do with advanced aircraft propulsion and maybe even space technology. But that's the point was that in terms of what we need to develop a interplanetary civilization, we haven't really got the propulsion systems we need to do that yet. And the Vasimir is, I think, has its strengths and weaknesses, but at least it's somebody trying to step up and say, let's try this. What I like about the Vasimir is that it lets you trade off thrust with what's called ISP, or specific impulse, which is basically how fuel efficient the engine is. So you can go with a higher thrust sometimes and then throttle back and get something that's sipping fuel on the way out. That's that's pretty exciting. And I don't really think the Vasimir is the final answer, but I'm glad NASA's funding a small project to look at it. They're of course, where they're putting a big chunk of money right now is in the Space Launch System, which is extremely controversial. It's not clear, and mainly because it's just going to cost so much. It's going to cost a lot of money, and you've got the Falcon Heavy coming along, which doesn't cost anywhere near as much and will deliver much of that capability. So there's there's a great deal of concern that the entire NASA budget will be sucked up into the SLS, and then you won't have money for anything else. And one of my favorite projects.
Yeah, NASA's really been marginalized.
Well, they're getting about what, $17 billion a year, if I'm recalling correctly, which is really less just inflation than they got 20, 30 years ago.
It's like the usual 1 or 2% per year. I think it's what they keep on getting, maybe a little more of the budget.
They don't get much budget, and they often have to make very painful decisions about what gets funded. And for example, one of my favorite missions, LISA, got unfunded. Another one, Terrestrial Planet Finder, got unfunded. Now the Europeans are picking up the LISA ball, I hope, and we'll run with it. LISA is looking for very low frequency gravity waves, which could tell us something about the earliest moments of the universe. So hopefully the European effort will proceed. Terrestrial Planet Finder would have been awesome. It would have been difficult, but awesome. And if they could have pulled it off, well, we're going to have to wait for that now. We don't have anything quite like that, and won't for quite a long time. So now let's can we talk a little bit about these fast radio bursts? Is anybody interested in that?
Yes, please do.
Yeah, I find why there's been 11 fast bursts that have been discerned, and only one of those has been proven to be some interference of microwave oven. But
no. The microwave ovens
determined, right?
There are 11 legitimate bursts that are known that are not thought to be from a terrestrial source. There was another group of things called the perytons, which were always suspected to be from a terrestrial source, and now it turns out they are. They are from it looks like somebody was opening the door of a microwave oven without turning it off first. And that's what, when you open a microwave oven, it cuts off, right? If it's running. And when it cuts off, you can get this kind of chirping RF signal that can leak over into the radio astronomy bands. And that's what they were seeing. So, but the fast radio bursts are a different animal. They do appear to be from a distant source. And
celestial.
Well, the first thing that they decided was that they were from a very distant source, because they have what's called a high dispersion measure. That is, the different frequencies of this pulse arrive at different times, which is something that happens to signals that travel through a lot of intergalactic medium. And they were getting high enough dispersion that they were calculating it had to be from outside the galaxy. But then a paper came out quite recently by three guys who are not astronomers, but are physicists who work on high energy physics, who, it has to do incredibly complex data analysis all the time. And they found a very interesting pattern in the bursts. Now, again, there are only 11 bursts. 10 of them are from one radio telescope. So it's early days. It's too early to conclude anything. But they found this pattern of discrete. They found that if you divide the dispersion measures by a certain number,
187.5
parsecs per cubic centimeter, yes, then you get they all line up on discrete multiples of that. And that is just weird. That does not make sense. So we either have
Indicating what?
we don't know. It's either we have
Intelligence?
possibly. In fact, the paper does speculate on it that at the very last paragraph, they kind of play that card, or they show you that card, but they don't really play it.
But now that we know the pattern, presumably we can look for more of the pattern.
That's right. And we should be detecting at least a couple of these a year. So if they fall on those same discrete multiples, the weirdness goes on, right? Otherwise, maybe, and they did an analysis showing how likely is it that, asking how likely is it that this happens by chance, and the answer is it's not very likely at all. So, but we are still
okay. But here's the question. Why is it all from one radio telescope source?
Well, there's actually two.
Isn't that weird? Is it looking at a particular place in the sky?
No, they're different places in the sky. But there is one of these bursts from a completely different telescope, the one in Arecibo in Puerto Rico.
Yeah.
And
the one 2012, it was picked up by Arecibo, I think.
Yeah. And that fits the pattern as well. So now, are we done with, and we're ready to conclude that somebody's trying to send us a signal? No, we can't. That would be extremely premature. But as we get more of but since the pattern's been discovered, now we're going to be looking, does it do the next bunch of bursts fit this pattern? And
how far could we push the extrapolation of the pattern?
How far does, right now, the farthest it goes out is 9 times. But and we
now,
don't have
why isn't SETI all over that?
They are. However, they are skeptical for the same reasons that I am, and that is there have not been enough different telescopes that have detected this. Part of the reason for that is that the folks at the Parkes Radio Observatory have really been trying to catch these. A lot of scientists may have detected them and then thrown them out. These things only last milliseconds.
But my understanding that they happened to find one, and they only found the additional instances by going back through past data that had been saved. So it's not like they were sitting there and 10 came to them while they were waiting. They found something interesting, and they went back to the data and found more instances of the same kind of signal.
Well, they did catch one in the act last year. They started looking for them.
One in the act. Right.
Yeah, and they could not find an optical counterpart or an X-ray counterpart or an infrared counterpart. So they were. It's really interesting. It could be a new type of astrophysical object. It could be lots of things.
Yeah, I was thinking about, when the quarks were discovered, remember there was a burst that came from quarks.
Well, quarks were theorized before they were discovered.
This could be similar to that.
Well, yeah, but quarks were never really, oh my gosh, what is that? It was an awful lot of theoretical work that said, there should be some kind of particle here. And then they started looking for them and found them one by one. And they're only known indirectly. You can't really actually grab a quark and put it in a bottle. But this kind of signal is it's going to be something. It's a story worth watching, and I'm going to keep watching it. I think the next few bursts that come in will be extremely interesting to see if they fit this pattern.
And if they come out of one particular point in the sky?
Well, they don't seem to, but it's hard to pin down a geometrical pattern. But one thing that is interesting is that, if this pattern suggests that they may not be all that, it's at cosmic distances, they may be in our own galaxy. And we're just misinterpreting why we're getting this dispersion measure. The dispersion measure is simply a measurement of arrival time versus frequency, or vice versa. So,
Yeah. Apparently, there's been a contradictory studies. Some of them speculating that, like you were saying, Paul, that the origin is intergalactic or and even close proximity stars. I think one of the studies were saying, and some other ones that are saying that the sources might be much more distant than that.
Well, some think it's neutron stars collapsing into black holes, or
Right. I read that. I was reading that.
yeah,
Too.
and all that is part of the normal process of trying to work our way through these things. I mean, remember when gamma ray bursts first came out?
Yeah.
Almost an analogous type of phenomenon. Nobody had any idea what they were, and it took a long time. And now we think kind of have a handle on that, but it's still, that took an awful lot of research and the launching of the Compton Gamma Ray Observatory and other satellites to try to nail down where those bursts were coming from.
And now we have a better understanding of the universe as a result of it.
Much better, yes, and we've caught several optical counterparts. That's part of the reason we understand it better. So we're probably about the same stage we were in the 60s with gamma ray bursts, with fast radio bursts. We just don't know. And at the time, there was speculation that we might be seeing something generated by an advanced extraterrestrial intelligence, because they just didn't make sense. But it turned out to be far more likely to be a natural phenomenon, and that's where we are now. Let's see.
That's interesting.
What else do you guys want to talk about today? I mentioned that. Go ahead.
No, I was saying that there's a lot of news that are coming through the pipeline, and I wish that I had a little bit more kind of advanced notice, because I know that this program is kind of impromptu in many ways, right? Because of the reasons that you highlighted. And but there are some stories. There was a very interesting story that came out today that I have shared on social media, but I am not extremely prepared or rather knowledgeable of the intricacies of it. So I don't want to go ahead and necessarily provide inaccurate information. But the gist of it is that some scientists have found that by studying a group of red giant stars, that that unusual their chemical composition did not demonstrate the age that would have been anticipated, knowing all that we know to this point. So basically, they're saying that the chemical signature is as though almost these red giants were frozen in time, and and really their age is not what it looks like right now. I mean, that's kind of the gist of the story. It was a very interesting story. I wish that I was a little bit more prepared to talk about it, to be honest with you, but it seems like it was a very interesting study. And I think that the bottom line is, and kind of this kind of a little bit links also to what we were just talking about earlier, that there's so many things in space exploration and astronomy and astrophysics that are I mean, that's the nature of science in general, right? Not just astrophysics, that almost on a daily basis now, theories that once were believed to be set in stone, right? They're revisited, and there's some new discoveries that places them into question. And I think that's an important thing, that is an important way the science operates. I guess that's just as a broad statement, I suppose.
Yeah. Well, yeah. Well, we can, red dwarfs are very important, right? Because they're something like 3/4 of all the stars.
Right.
And so, and we'll dig into this in a future episode. But when you look at the Drake equation,
yep,
most of the stars that you're talking about are red dwarfs, and there's been some really interesting work done lately on whether or not you could have a habitable planet about a red dwarf. Because the nice thing about red dwarfs is they last for tens of billions of years.
Did you watch the recent NOVA program on alien planets revealed, where they talked about the possibility of tidally locked planets around a red dwarf star having a habitable zone that's like a ring around the planet between the night side and the day side.
No, I didn't watch that, but yeah, I'm familiar with the idea. Yeah, and you would get atmospheric circulation that could keep a pretty large part of that planet habitable. Because we should explain, any planet that's close enough to a red dwarf to be not a frozen ball of ice is going to be tidally locked. It's going to, in other words, it's going to present the same face to the star all the time, just like the moon presents the same face to the Earth all the time. And so the question is when you have this sunlight shining on one side of the planet and the other side of the planet totally dark, is any of it habitable? And that is a very good question. And how wide is the habitable zone around a red dwarf? Is it? And a paper by Jill Tarter and a few other people that came out about 8 years ago suggested about 5% of the planets around red dwarfs were habitable. Yeah. So
are red dwarf stars mostly population 3 stars, the last, with high metallicity content, or do they range from, have
they range quite a bit, but they're the majority of the stars, even the newer stars. Now the newer red dwarfs tend to be flare stars. The younger red dwarfs, they're not. In other words, they're not very nice places to be. But the older red dwarfs, which are probably population 1 or population 2, are pretty stable, and that's something that's under a matter of current study. Just how habitable are red dwarfs?
As a matter of fact, I think I have to stand corrected, and that kind of is a testament to me not being prepared on all of these. I think that these was red giants, actually, not red dwarfs, in particular for the particular study that I was referring to. So I want to stand corrected on that one.
Okay.
Yeah, but it was red giants. Okay, so
both red giants and red dwarfs have their place in galactic ecology, and they're related to each other in the large scheme of things.
Yeah, right. Red giants are not main sequence stars, though. They're stars that have.
The point of the study was that they found this discrepancy between the chemical composition of these stars, of this group of stars, and what the real age, and found that just by looking at the chemical compositions, the stars would indicate an age much older than the real age of these stars, which turned out to be much younger. And the way they found the actual age was that you're using a technique called astroseismology, which I think it looks at the pulsation frequencies, of this, I believe, of the stars, I suppose, to figure out their actual age.
And what are the estimated ages of these stars?
I haven't seen that part of the article. I just I don't know if there was actually indicated in the article, to be honest with you. But the point, the gist of the article, the point of the study was that their chemical clock doesn't represent what the age of these stars are, and this kind of has also implications regarding the actual galactic history of the Milky Way. Because I think that some of the studies, because some of the studies are related to one another, and the age of the stars, of certain population of stars, gives certain indication to some of the age of the galaxy in general. And so one of the things that the study mentions is that this is going to have implications also in our understanding of the age of the galaxy itself.
Well, they're aging stars, right? So wouldn't it be interesting if their age changes as they're diminishing? Like it increases or something? That would be an interesting thing to look at if their age changes in relation to how quickly they're diminishing.
Well, we know that the very old stars have very little metal in them because they formed early in the universe when there wasn't a whole lot of metal available. In fact, when I was a student, there was a problem that was unsolved at the time, which was that some of the stars that we know about seem to be older than the universe. That problem has since been solved. I think, at least to most people's satisfaction, that those stars are very, very old, but not older than the universe.
Universe.
Yeah,
that would be a very interesting paradox. That would pose a pretty interesting paradox.
well, I mean, obviously, we were wrong about something, right? If we think that the stars are older than the universe, that doesn't make sense. So,
right.
Now, these are the stars that you find in globular clusters that have been relatively isolated out there by themselves for a very long time. They are very old stars that should live, they're small, relatively low mass stars.
Right.
They live a very long life.
But Paul,
Yes.
Do rates of decay change over the life cycle of a celestial body?
I'm not sure you mean by
Like,
decay.
I mean, this is a stupid example.
Decay
Well,
of
like, say, for example, a dog, this is the best way I can put it. A dog, when it gets to be a certain age, it doesn't age 1 year by 1 year. It's not a correlation. When a dog gets to be a certain age, 1 year then becomes like 8 years of life. So that certain celestial bodies at particular points in their life cycle, for lack of a better term, they might age or decay or whatever at a different rate because of a different
Well,
part
what
of its
happens
life
is
cycle.
when a star first forms, it forms very fast in millions of years. It then sits there for billions of years, just being a happy little star. And then it goes through another period where the star dies, which takes a shorter time than that, but typically, and this, I'm talking about a star like our sun, which would be, hundreds of millions of years. It would slowly lose mass and then decays into a white dwarf. Big stars live very short lives and blow up spectacularly. And small stars, which is most of the stars that we know, live very, very long, stable lives. Like you said, almost as long as the universe and could be, and could live many billions of years beyond the present. And they will just gradually become white dwarfs over time, but over a slow process. So there's what they did is they went out and looked at all the stars, astronomers looked at millions of stars, and they lined up how hot the star is versus how bright it is. And the really big stars are both hot and bright, and the small stars are well, not only hot and bright, but they're blue and bright, right? And the small stars are red and not very bright, which is why when you go up and look at the night sky, you don't see millions of stars. You see thousands of stars because most of them are too dim to see. And the red stars are the majority of the stars, and they last a long time. And so we're, and our stars is kind of in the middle. The sun is a sort of a mid-range star. It's not really heavy and it's not real small. And so
in the middle of the Hertzsprung-Russell diagram.
Yeah, it's what we call a sun-like star. It's not surprising. And it turns out to be about 15% of the stars are sun-like. And and a lot of the efforts in finding Earth-like planets are based on sun-like stars, but the reality is most of the stars that have planets are going to be red stars. And if you're looking for something that a civilization could develop on, you want it to be stable for a very long time, because to get to complex life, we know our own example. It took, from the time life started to the time life was complex, was about 3 billion years. Most of the history of life was algae.
Dead simple.
Yeah.
Pretty much.
I mean, it was sort of evolving the complex cellular chemistry that would later serve as more complex life. But you didn't have fish, you didn't have octopuses, you didn't have lizards, you didn't have birds, you didn't have monkeys. So
not until the Cambrian explosion about 500 million years ago.
Yeah. So
Right, and
most
then
of,
even in our life cycle, you find times where it just went along kind of slow, and then bam, there was this accelerated growth period, and then it slowed down again, and there was another bump. That's how life pretty much went here. So it hasn't just been this slow linear increase. I don't think many things are. It's the same with these.
Yeah.
Yes.
And there's the biologists are still arguing about that, but it's pretty clear that life was real simple for a very long time. Then something happened to make it a lot more complex. And then
there's even a term to use to describe that called the boring billion. I caught that from Robert Hazen's book on the history of life. So the period when life is dead simple and changes almost not at all for a billion years, that's the boring billion.
Yeah, and so we don't know if that would be the pattern everywhere, but if you assume that it is, then you need stars that are going to be around for a long time to evolve complex life. Even if it's not smart monkeys, it could just be, it could be whales. But,
smart slime.
Smart slime, whatever, and it's an interesting question whether smart monkeys are inevitable or a quirk.
This is a good conversational loop. We kind of went back in circle to the beginning, to what we were talking about. And again, I think that one of the things to keep in mind is that we have to think. We kind of think in terms of what the evolutionary history of Earth is, right? And because that's all we can base ourselves upon. But there's nothing that, in my opinion, nothing that prevents a different evolutionary history altogether taking place on another hypothetical planet. So then, it means maybe that the evolutionary times before an intelligent civilization arises and emerges might be much shorter than the times that have occurred here on Earth.
Or much longer.
Or much longer. Sure.
That's why it will be so important for us to check for biochemistry on Mars or the moons of the outer solar system. As Carl Sagan said in his Cosmos, we can only, once we have another sample of life and can compare it to our sample of life, we're going to learn a lot about biology very quickly.
Right.
Yes, well,
right.
See, it depends on what it's exposed to. Just like the. Sorry, Paul.
Well, I was just going to say something that I've said many times before, that if we can find evidence of what's called a second genesis, that is, life that arose completely independently from the inner planets, and I'm not so sure we can say that about Mars, Venus, or Earth because there was so much interchange of data, of material. But if you go out to Enceladus and you find a biochemistry there or Titan that is completely different from anything that we've ever seen before, it indicates that life arises wherever it can, or at least often arises whenever it can. And that is the fourth term in the Drake equation. That's an important thing that we're trying to nail down is when life can arise, how often does it arise? My own gut feel, which doesn't count as science, is that the fourth term in the Drake equation is 1.0, but I don't really know that. And the evidence would be if we found something on Enceladus or Titan or something that showed that, you get complex chemistry, and then you get it self-replicating.
Right.
And that's what makes it so tantalizing, because that's within our technological graphs right now to go to those moons and sample that biochemistry if there is any there, at least to sample the surfaces or their oceans or their atmospheres and see what we can find.
Yeah,
right.
The Titan.
Since nothing. I was going to say, there's nothing that exists that is not impacted by everything else around it. So it's what bodies have been exposed to. It could very well be that this body of ours was exposed to something that created and accelerated growth for whatever reason, and that everything out there, every celestial body in existence at some point in time is impacted, and that deposits or exposes this body to something that it hadn't had before, perhaps. So that could explain how these spurts happen, is an exposure to something that is an accelerant of some sort.
A selection pressure.
Right.
I think that the Drake, speaking of the Drake equation, I think it's already, it's already very intriguing and exciting to me anyway. The fact that we have discovered so many confirmed exoplanets in recent years, and already how much that affects the Drake equation and its percentage values. But think about what discovering life even on one of the bodies of the solar system would signify to the entire the Drake equation itself. Not just the fact that itself that you have found the presence of life on another on another body outside of Earth, which in and of itself it's a big discovery, a historical discovery. But that would
but isn't it statistic?
Yeah, that would also exponentially increase the value of the Drake equation, because now all of a sudden, as soon as you know that something outside of Earth has life, the probability that life is would have emerged on another celestial body, it's kind of it rises up exponentially.
Yeah.
I don't know if it makes.
But don't you think it's statistically inevitable? It's statistically inevitable that there's going to be life out there, really, isn't it? That's what the Drake occasion.
No, I don't know that it's inevitable statistically. That's why we have, we have this probabilistic, equation such as the Drake equation. That's what we're trying to ascertain. What is the probability?
Well,
but
even if it's even if it's inevitable, if the probability is very, very low, then we're unlikely to have another civilization out there that we can talk to, and that so.
Right.
And all you have to do is sit down with a spreadsheet and go through the Drake equation, and just play with the numbers. Now we know the first three terms pretty well, but there's four terms that we don't know, and you will see with some pretty reasonable assumptions that you can get to where there's only one civilization in the galaxy.
Right.
I'm sorry. I have to disagree with that. I have to disagree. I'm Patrick. Sorry, I'm late. I have to agree more with Marsha. The probabilities are very high. However, they're much higher for any life at all. And then as you move up the ladder of more sophisticated life or more complex life, the probabilities go down. As far as there being another civilization out there, the probabilities are much lower, but they're certainly not down to one. They are out there. However, the possibility and the probabilities of either us going there or them coming here are almost nothing. But, it takes a lot. We all have to behave. What do you call it? Adhere to the laws of physics. The laws of physics are the same everywhere, and there really is no such thing as warp speed. There really is no such thing as light speed, traveling at light speed or greater. So we all have to abide by those physical laws.
The laws of physics, as we know them now, you can't say we know everything there is to know about physics.
No, but
we're
really does
severely
equal MC
hampered
squared.
by the lack of knowledge in physics.
That's true, but E really does equal MC squared. You wouldn't be able to use GPS without that. And the fact is that the faster you go, the more massive you become, and it becomes it really does mean a lot. And E equals MC squared really does explain a lot more than people realize. So I'm just going to go with that for now. I mean, there may be vast discoveries that we might make in the far future, but as of right now, of course, there's life out there. There's probably life everywhere out there.
Right.
I mean, even in our own solar system, they're finding all kinds of oceans and waters and different moons. But as far as civilized life, then the probabilities go down. But I still wouldn't say down to 1.
Right. Well, in the future, I think near future, we will walk through the Drake equation, term by term, and we'll see what we think, where the numbers come out. My analysis of it, everything depends very heavily on the last term. Nick's more of an expert on that than I am, but how long a technological civilization that wants to and is able to communicate with us will endure. And
who's the guy who writes all kinds of books? His first name is Timothy. He's written a lot of science books.
Ferris.
Yeah, Timothy Ferris. In his television show about life in the universe, he illustrates that really nicely by actually showing a Christmas tree and showing the lights blinking on and off. And if you make them blink on and off pretty seldom, each light is on alone. And if they stay on longer, or there are more of them, some happen to be on at the same time. It's a really beautiful illustration of the idea of that last term, of the length of the life of a technological civilization.
Yeah, I thought that's an excellent metaphor. Okay, guys, I think I really appreciate everybody showing up at the last minute and filling in when we seem to have lost our guest and the rest of our panel, but hopefully this won't be the normal procedure. But I think we'll wrap it up now, and hopefully see you guys, all of you back soon. So I'd like to thank Marsha and Marsha Barnhart. Say goodbye, Marsha. And
goodbye. It's been great. Thank you.
And Ciro Villa.
Yes, thank you so much, Paul. I appreciate the invitation again and the opportunity to be on the show.
Nick Nielsen.
Bye, Ciro.
Thank you also. We greatly appreciate the opportunity to be here.
And Patrick, did I get that right? Festa? Patrick Festa?
Yes, thank you. And I'm sorry that I came in the last minute and I'm already leaving.
Oh, we'll catch you again soon, I'm sure. Okay.
If there's any way I can get the invites more visible, I don't know. Sometimes I think the invites just suddenly pop up out of nowhere, and Google Plus is hard to navigate. I think I just see them all of a sudden, and I popped in when I saw it.
Okay, well, I'll work on that. Right now, I'm not sure how to do it, but if you have a Gmail account, it should go to your Gmail.
Yeah, I still have my old regular email account. I still haven't changed it to Gmail, but anyway, I'll try and follow somebody. Let me see. Maybe if you're which one are you? You're Paul. Maybe if I follow you or something, and you're
yeah,
okay,
I'm not sure. We'll work on that.
If you have Unseen Podcast in your communities, you should be able to see it. Just make Unseen Podcast a community.
Oh, he is in the communities, yeah. So
yeah, that's how I got it.
But the event is not in the community.
Okay.
It's because we only invite a subset of the community on a given.
Oh, for invitees.
Yeah. So
that's right. Yeah.
Actually,
okay,
I already have you in 3 of my circles, so I guess that's not going to work either. I already have you in following and the other 2 circles. So
okay. Well, I'll work on that for you, and we'll because we want everybody to be able to handle that easily. And I think the trick is to have a Gmail account, and it'll automatically just come. You get an email. Okay. Well, again, thanks to everybody, and we will see you again in the very near future. And this has been the Unseen Podcast, episode 2, and we'll see you again in 1 week with episode 3. Bye-bye, everybody.